So now it is time to introduce Aric with my great pleasure. He's an associate professor of analytics at Institute for Advanced Analytics in North Carolina State University. He grew up in Rochester. It's a great, nice place near the lake. Aric is passionate about helping people solve challenges using their data. He helps to design innovative programs to prepare a modern workforce to wisely communicate and handle the data-driven future at the nation's first Master of Science in Analytics degree program. So you can also talk about this, Aric, if you want, and if people have questions, they can ask here or later as well. And he teaches courses in predictive modeling, forecasting, simulation, financial analytics, and risk management. Previously, he was director and senior scientist at Elder Research, where he mentored and lead team of data scientists and software engineers. As director of the Raleigh, North Carolina office, he worked closely with clients and partners to solve problems in fields of banking, consumer product goods, healthcare, and government. He all holds BS in economics, as well as BS, MS, and PhD in statistics, all from North Carolina University. This was his favorite, this is where my wife is from, actually, my second home. So that's why I have a special interest in North Carolina. Now I don't take long and let Aric start his presentation. Thank you, Aric, for being here. Appreciate your time.
Sure thing. It's an absolute pleasure. Thank you all so much for having me. Thank you very much for the wonderful introduction, Murat. It's also something when it comes to LinkedIn, I have a unique spelling to my name, so I'm not a hard person to find. Feel free to reach out to me on LinkedIn. More than happy to connect with anyone as well. But thank you so much for having me today. My goal today is to talk to you guys about modern approaches to fraud and anomaly detection, or sort of the informal way I like to describe this is finding that needle, right? We always hear that analogy of trying to find a needle in a haystack. All right, well, let's try and find modern approaches to being able to find that needle in a haystack. So really, I want to be able to just give you guys a general idea on how we can do this. Like I said earlier in the chat, more than happy to share the slides as well as some generic code on how to be able to apply some of the techniques we're going to learn here today. So first things first, let's talk about anomalies, okay? If we're going to do anomaly detection, we need to be able to answer the question, what is an anomaly? Well, formally, again, going to Oxford Dictionary here, the idea of an anomaly is basically something that deviates from what we would expect, something that deviates from standard or normal. In fact, in my experience, a lot of what we've had to think about in terms of anomaly detection is how we define normal. Once we define what normal is, it's a little bit easier to be able to try and find things that are abnormal. And that's what our goal is in anomaly detection. So why do we even care? Why should we even detect anomalies in the first place? Well, a lot of times anomalies get in the way of decision making. Maybe it leads us to incorrect decisions. Maybe it leads us to out-of-date decisions. But essentially, we're trying to find these anomalies, these outliers, before they become too much of a problem in the analysis that we're doing, in the data that we're examining. Again, bottom line, in the decisions that we need to make. Anomaly detection techniques are used in a variety of fields. But in case you're not in one of these fields, anomaly detection is also used in just cleaning any data set when trying to understand if something seems to be out of place. But specifically, anomaly detection is really important in the fields of monitoring health of computer systems, again, trying to see if things are going out of line, especially around cybersecurity threats. What happens if someone is attacking the system that we have? Or along the lines of fraud detection, trying to discover fraudulent claims or fraudulent transactions. That's really why we care so much about detecting these anomalies. And there has been a large evolution in the space of anomaly detection over the years. Everything from more probabilistic and statistical techniques like Benford's Law. Benford's Law is actually in the United States still admissible in local, state, and federal court. We also have the idea of z-scores, the interquartile range rule. If we were going to go to multivariate ways of looking at things, Mahalanobis distances. But now we're moving more into the machine learning world and trying to be able to get more modern day approaches to things. Not that any of those statistical and probabilistic approaches are bad, but there are just different ways of being able to view things, especially again in a multidimensional space. That's where things like local outlier factor, isolation forests, and even CADE, which is short for classifier adjusted density estimation, comes into play. Now, the reason I love these three techniques specifically, and the reason I want to talk to you about these three techniques today, is because of the fact that they actually got their roots somewhere else. The local outlier factor is built off of k-nearest neighbors. Isolation forests have come from the world of tree-based algorithms like random forests and gradient boosting. CADE was actually originally designed to be a kernel density estimation. In fact, a lot of times in the anomaly detection space, we find things in other areas that actually work really good for what we need to do. All right, so that gives you a little bit of a premise on what we're going to be looking at. We're going to be looking at these three approaches here in this talk today. Now, what data set are we going to be using to do that? Well, I'm just going to use a basic fraudulent data set. So I'm looking at a healthcare insurance data set here. And we're looking at income of individuals with healthcare insurance, specifically actually life insurance. And then we're also going to be looking at the coverage to income ratio for these individuals, with the premise being that if you have a lot of coverage but very low income, aka a high coverage to income ratio, that may be abnormal. Same kind of idea with just income itself. Maybe your income that you have may be abnormal in comparison to other individuals in our data set. But not just looking at those variables individually. We want to look at those variables in combination with each other, which is the scatter plot you see here. On the x-axis, you can see varying levels of income. On the y-axis, you can see that coverage to income ratio. So in our data set, you can see people with high incomes, with high coverage to income ratios. But I want to look again at the combination of those to be able to find potential anomalies. Now, by looking at this, you can probably eyeball some individuals that you're like, these people I'd probably like to investigate further. But this is just a simple example with only 2 dimensions. What if we had many more dimensions than this? How can we use algorithms to be able to help us find these anomalies? Well, let's talk about that. The first one we're going to look at is the local outlier factor, also called LOF. Before understanding the local outlier factor, though, we need to understand what it was built upon, and that is the idea of k-nearest neighbors. You guys may have heard of k-nearest neighbors before, but as a quick refresher, the idea of k-nearest neighbors is to basically look at the average distance each point is away from its nearest points. How many nearest points? K-nearest points. So for example, the highlighted dot down in the lower right-hand side of this plot, the one that's actually filled in all the way, if I wanted to look at its 5 nearest neighbors, the dashed lines are connecting those 5 nearest neighbors to the dot of interest. Well, one way to be able to look at that dot of interest is to look at the average distance that dot is away from its 5 nearest neighbors. This is helpful in the world of clustering to find observations that are similar to observations of interest. But it's also helpful in anomaly detection. What if we find points that aren't really close to anything? However, k-nearest neighbors does a great job of detecting what we call global outliers, points that are far away from the overall pattern. However, k-nearest neighbors does not do as well of a job at detecting what we call local outliers. So you can see here on the lower right-hand side, we have 3 observations that are highlighted as global outliers. Really, those 3 observations look to be different than the main data cloud that we have. However, even inside that main data cloud, there's a couple of points on the upper right-hand side, on the lower left-hand side of that main data cloud, where they really don't look like the rest of that data cloud. They are potentially what we call local outliers, points that maybe not globally are different, but locally may be different. In fact, look at the 3 global outliers. 2 of them are really close. One of them is still a little bit off from the others. So that may be in itself, again, a local outlier. So let's talk a little bit more about this local outlier factor. The idea of the local outlier factor is this. I'm going to explain it in words, and then we'll move into things more visually. I think visual explanations may be a little bit easier here. But some people see things better in words, so let's talk about it that way. The local outlier factor really is just a ratio. It's a ratio, which remember is just a comparison, of the average density of the k nearest neighbors of an observation of interest compared to the density of that observation of interest itself. Okay, hold on. What does density even mean? Well, what I mean by density here is essentially this idea of reachability, or actually the inverse of reachability. It's essentially how far do I need to travel to reach the nearest point? So the less dense means we need to travel further. So that's the idea of density. Again, the bigger the density, the less the density, the further away that point is from other observations. Again, it may not be easy to see in words. Let me try and show it to you visually. What I've highlighted here, again, with that same point of interest down to the lower right-hand side, is you actually have this density. What it really is a circle. I wish I could explain it in anything more complicated, but it's not. It's basically a circle. It's a circle, though, with a radius. That radius is the distance to the 5th nearest neighbor. Here, again, we're looking at 5 nearest neighbors as sort of our sort of baseline. Coming back here, we identified the 5 nearest neighbors here. But now what I want to do is I want to look at the 5th nearest neighbor, the observation that is 5th furthest away. So again, taking a look here, I'm going to try and highlight it here with my mouse. You have this observation that's the closest, the second closest observation, the 3rd, the 4th, the 5th closest observation right here. So this circle has a radius that is equal to that 5th observation's distance away. All right, so I want you to visualize this circle as the density. What I'm also going to do is I'm going to look at the densities of those 5 nearest neighbors. They're highlighted here by these circles. Now, this is where things become a comparison. I want you to compare the size of this circle to the average size of these circles. So again, it's a little bit different. You have to sort of take an average in your own mind. How big would an average circle be if I were to look at the averages of these 5 circles? So I have these 5 circles. I look at the average, and I compare that to this circle here. Okay, it looks like this circle is bigger than the average of these 5 circles. So this point has a potential of being an anomaly. Let me pick another one. Maybe it'll make it easier to see. Let's take a look at this observation here. So taking a look at this observation, again, I want you to visualize the circle. Again, formally, the idea of this circle is this is a circle with a radius that is as big as the distance to the 5th nearest point. So I'm looking at a circle with this radius. I'm going to take those 5 points that are nearest to this initial observation of interest, and I'm going to look at their densities, their circles. Again, I want you to take a mental picture of these circles here, and I want you to think about the average size of these circles. Compare the average size of these 5 circles to the size of this circle. Again, this circle is bigger than the average of these 5. That would imply this initial point is a local outlier, or at least has the potential of being a local outlier. That's the idea of a local outlier factor. That's the idea of density when we're talking about these things. So let's take that initial set of data that we were looking at earlier. Again, we're looking at income compared to the coverage to income ratio. This is the initial scatter plot that I showed you all. What I want to do is I want to scale the size of these dots by their local outlier factor. Oh, let me go back. Let me go forward. The smaller dots are less likely to be local outliers, while the larger dots are more likely to be local outliers. Again, take a look at what we see. We see something stick out like a sore thumb on the lower right-hand side, right? That observation on the lower right-hand side that initially just appeared far away from everything, well, it is far away from everything. It is not only probably a global outlier, but it's also a local outlier. And we can see, again, different size dots depending on how far away observations are from each other. So that's the idea of the local outlier factor. One technique down, two more to go. Let's talk about isolation forests. Now, of course, if we're going to talk about isolation forests, the very first thing we have to talk about is what in the world is an isolation tree? I know, look, we're math people. We're not the greatest at coming up with creative names. So we have this isolation tree that builds up to these isolation forests. Essentially, an isolation tree is really going with this idea of a tree-based algorithm to isolate observations. With the general notion being this: the easier it is for me to isolate an observation, the more likely that that point is going to be an anomaly. Perfect. So when looking at the nearest point, or I'm sorry, when looking at trying to isolate these observations, what we can do here is, again, just randomly pick an axis. So we only have two axes here, but we're going to randomly pick one of the two axes. Here we choose the x-axis. And we're going to put a random line on that axis. There's no statistical test here. There's no Gini coefficient if you're familiar with decision trees. There's nothing along those lines. All we're doing is picking a random axis, and we're picking a random spot on that axis. And we're just slicing our data into two pieces. So take a look at what we've done. We've isolated a lot of the observations on the left-hand side, while we've put 5 of the observations on the right-hand side. Perfect. So now we're going to do the exact same thing, except we're going to do it in each half of our data. So we take the two halves of our data. Within each half of that data, we're going to, again, pick a random axis, and we're going to pick a random spot to split. Well, let's take a look at the half that was on the left-hand side. So again, the left-hand side here, pick a random axis. We're going to pick the y-axis. Perfect. We're going to pick a random spot on the y-axis. And again, now we've isolated ourselves into two pieces. Awesome. We're going to do the same thing on the right-hand side. Pick a random spot here on the y-axis, and we've isolated ourselves again into two pieces. But look, we've been able to successfully isolate this one observation of interest. It only took 2 passes through the algorithm to be able to isolate this observation. Well, perfect. So that observation's been isolated. Now we still have a lot of other observations to go. And now we have 3 other pieces of data to look through. So we're going to do the same thing. Again, in each of those 3 pieces of data, we're going to pick a random axis. We're going to randomly slice our data and split it into 2 pieces again. So we have these 3 pieces that have now become 6 pieces. In this third piece that was over here, we've again split it into 2. Oh, look, we've isolated another observation. And so that's sort of the idea. We're going to keep isolating these observations one at a time by randomly splitting off different pieces of our data set. That's all an isolation tree is. There's not a lot of intense math behind it. It makes it actually really easy. The downside, though, what if we get lucky? Right? So what if we get lucky and accidentally just split something off really quickly, or unlucky and don't split something off really quickly? So this isolation score that we have, which again, the way we calculate an isolation score from an isolation tree is we basically normalize it to be between 0 and 1. The closer to 1, the easier it was, the fewer splits that were needed to be able to isolate. The closer to 0, the less likely it's an anomaly, the harder it was to isolate. And so in this kind of scenario, again, maybe we get lucky with the isolation score for that one observation in the upper right-hand side. Perfect. Well, that's why we have an isolation forest. Again, not very creative, but we'll take it. We're basically going to build a lot of isolation trees over and over and over again on completely different random splits, on completely different random dimensions. Maybe the second time through the tree, that point in the upper right-hand side wasn't isolated until the fourth or fifth step. And that's sort of the idea, is we're trying to get an average idea of how long each point takes to survive this process of splitting trees randomly. Once we do that, we have an idea of a score. We have this average score across all of these isolation trees. That gives us the score from the isolation forest. Perfect. So let's go back to our chart again. Same idea, same scatter plot. Income compared to coverage to income ratio. Let's see if we can split these things up. Again, now I've highlighted things here completely based on the isolation forest. So this is their isolation forest size. Let's go back here. Every observation treated equally here. When looking here, the bigger observations are the ones on the outskirts, right? The ones that we would probably be able to isolate easier. The ones that are harder to isolate, look in the lower left-hand side of this plot. Look how small those circles are. Because they're so tightly packed in a dense cloud, it's very hard to isolate them, whereas all the circles on the edge are much easier to isolate. That's the idea of the isolation forest. All right. Let me go ahead and I see that we have a couple of questions in here. Sorry, I've missed those. Let me go back and let me make sure I answer these couple of questions, and then we'll move back into the third technique. So it looks to me as if the nearest neighbors are types of compact covers of the data set. So the overall process is to pick a cover, then compare the effectiveness of that, scheme. Essentially, you can think about it that way, right? So essentially what we're trying to do is we're trying to isolate out, Edward, trying to isolate out small pieces of our data, right? We're trying to figure out which observations are trying to be able to be sort of closely grouped together. Except now we're going to use that close group together to try and figure out, are they closely related to each other, or are they far away from everybody else together or separately? And that's sort of the idea of that local outlier factor. Speaking of local outlier factor, we also have this idea of, another question that came in. Do you take the ratio of one density with the average of the remaining 4, or do you take the ratio of one density with the average of all 5? Does the difference between these two make any difference? Yes. So when I'm looking at the k nearest neighbors, so if I'm looking at the 5 nearest neighbors, I'm not including the point itself. I'm not including that point. I'm looking at the 5 other ones to be able to do that. So when looking at the 5 other observations, I'm taking the average of the 5 other ones, the 5 nearest neighbors, not sort of the 5 including the original point, the 5 not including the original point. So hopefully that answers that question as well. Got another question that came in. What has been a better example of an isolation forest application in a data set than this? I can use my eyes to detect the outliers that are here. You're exactly right, Athena. I think the best application here is when we go beyond 2 dimensions, because you're exactly right. We can easily eyeball things in 2 dimensions. And the reason I want to show you that graph in 2 dimensions is sort of to give you that confirmation of, oh, yes, well, that makes intuitive sense on why this would be an outlier, why this wouldn't be an outlier. But now let's imagine I had 15 variables and I had multiple dimensions that I couldn't visualize easily. We can still slice and dice that data any way we would like through an isolation forest. We're not limited to having to do this only on 2 dimensions. We can do this on multiple dimensions beyond 2, which might make it a little bit easier to be able to find that outlier, that anomaly, beyond what the eye can normally see. So hopefully that helps. All right, 2 techniques down, 1 to go. One of my favorite techniques, CADE, also known as the classifier adjusted density estimation. So what essentially is CADE? It's actually an algorithm, but it's a very loose algorithm. It was originally designed to actually do density estimation. Think kernel density estimation, trying to understand different distributions and trying to be able to estimate those distributions based on the data that underlies them. However, people in the fraud and anomaly detection space have really gotten value out of this algorithm in being able to detect things that don't belong, things that are outside of the normal pattern of this density that the data was trying to be able to be estimated with. So let me give you the process of CADE, again, in words, and then we'll talk about it visually. Here's the actual process on how we look at CADE. Essentially, we're going to take all of our original data. We're going to label that original data as not anomalies. They're not outliers. They're great. If you were thinking about it as a binary, label them all as zeros. That's essentially what we're going to do. Now, yes, I know that there are anomalies probably scattered in there, but what we want to do until then is just label everything as not an anomaly. What we're going to do is we're going to take that data and we're going to actually replicate it. We're going to create new observations, same size as the original data, but all of the variables now are uniformly distributed. So it's not really looking anything like the original data we had. Let's imagine we had something like age, and age wasn't uniformly distributed in our data. Maybe it was something that was right skewed in our data. What we're going to do is we're going to take the bounds of age and we're going to build a uniform distribution for that. Now, all of these new observations that we're looking at, we're going to label these new observations all as outliers. So we have our original data, the zeros. We have this new fake data we'll call the ones, and then we're going to merge everything together. Well, now we have this combination of fake data and real data. What we want to then do is we want to actually apply a classification model on top of this. So when applying a classification model on top of all of this, we're going to try and predict that fake data. We're going to try and predict those ones. We're going to try and predict those anomalies, those outliers. And then what we're going to do is we're going to score our original data. Well, why? Why would that be helpful? Think about it this way. If our original data is scored and there's an observation in the original data that looks more like the fake data than it did the original data, then you know what? That's probably an anomaly. So again, if I was to build a probability model, a classification model to try and predict original data versus fake data, and I use that to score my original data, those high probabilities are going to be where that original data didn't look like the rest of the original data. Again, it's that idea of if something looks closer to fake than to real, then it probably doesn't look very real at all. Here's a visual representation. Again, let's imagine we have some distribution. Here, let's imagine a nice pretty bell curve. That's our real data. When it comes to the idea of this fake data, again, we're going to build a uniform distribution in the same bounds as our real data. So what is this algorithm doing? All it's trying to do is it's trying to predict fake data. Well, what observations in the real data are going to look like the observations in the fake data? Oh, wait, they're going to be the ones that are sort of on the outskirts, that are on the edges. The anomalies in the real data are going to look more like the fake data than they are going to look like the real data from which they came. Again, the beautiful part about CADE is we're not just doing this with a single variable. We can do this with as many variables as we want. Again, in a multidimensional world. That's where we can add in more value. So again, I'm just going to show you a two-dimensional world because it's easy to visualize. But we have this idea here in this two-dimensional world where we have income, again, compared to coverage to income ratio. So when looking at this and then scoring it with CADE, now what do we see? Again, maybe a little hard to see. Let me go back. Let me go forward. Let me go back. Let me go forward. You a little dizzy yet? Okay, so the idea here, again, the observations that are on the outskirts seem to, again, be flagged as ones that are far apart from the rest of the data. But also, I want you to look at the lower left-hand side. The lower left-hand side has some small circles in it, again, ones that are part of the group. But even look at the edge of the lower left-hand side. Look down here. Points we've never really thought about before, but points that CADE is detecting. Because CADE says, you know, it's kind of on the outskirts of what I normally see. It's not in the middle chunk of the data. It's easy for us to sort of eyeball all of these anomalies, but who's to say these points along the edge aren't also potentially anomalies? And that's the value what CADE can provide. Again, on a multidimensional scale, it can go beyond what we have here. I have a couple more questions that have come in. Let me go ahead and answer those. So is there a situation where users would not know what K should be? Again, going back to the idea of local outlier factor and K nearest neighbors. You can play around with what K you want to be able to adjust to be able to see how you can isolate an observation. So the bigger the K is, the more your points you're averaging together, the more points you're bringing in. So it really is, you can almost think about it like a tuning parameter. Try out a couple different Ks, see what outliers you find in that sense. Another question, do you use any metric to calculate the success of an isolation forest? Oh, so no, the isolation forest itself has a metric. It's really sort of that notion of how many slices it takes to be able to isolate a point. What we're doing is we're just normalizing that metric to be between 0 and 1 to make it easier to compare. So once we know how many slices it took across all of the things that we have, we can normalize it out. We can normalize it out. So how effective are these different approaches at distinguishing between data points that are actually part of the tail of a bell curve distribution versus data points that are actually anomalous? Well, and that's sort of the point, Brett, is going to that notion of what is an anomaly? You know, if we're looking for what is an anomaly, we have to first figure out, again, what is normal. So here in this example that I drew, let me go back a slide. Here in this example I drew, it's really nice to sit there and say, oh, okay, well, this is going to be separated in terms of tails on a bell curve. But again, maybe you have things in a multidimensional space. Going back to this plot all the way back, coming back a little bit further to a plot here. In a multidimensional space, we may not have a nice, pretty bell curve. We may just have some isolated points in different areas. And so that's what we're looking at. In some dimension, we're trying to find places that things are just inherently different. And that's how we're trying to be able to isolate things. But you're exactly right. It depends on what normal is to determine these things. Perfect. So let's go ahead and wrap it up. So like I said, there's so many different approaches to anomaly detection. The classical probabilistic and statistical approaches, as well as more modern machine learning approaches. But those machine learning approaches actually typically come from other areas. They have their foundations elsewhere. That doesn't mean they're bad. It just means that they're different and that people have been able to use those ideas to be able to help them answer the questions that they had. Local outlier factor came from K nearest neighbors. Isolation forest came from tree-based algorithms. And classifier adjusted density estimation actually was originally used to be a kernel density estimation. The best part is most of these are easy to implement. I've just given you some examples here using Python. Again, they can be implemented in R, Python, a variety of different softwares. But local outlier factor as well as isolation forest actually already have built-in functions in scikit-learn. So you can specify some things as you see here quite easily. I've got a data frame. It contains, here are 2 variables, but you can have as many variables as you'd like. But here I have the 2 variables we looked at, income and coverage to income ratio. And we were looking at the local outlier factor. Same thing when it came to isolation forests. We have our 2 variables. We can build an isolation forest. Here I used 500 isolation trees to build that forest. Either way is fine. That's sort of the notion. Now, CADE, on the other hand, is a little bit harder, not hard, but harder to implement. I haven't actually seen anyone actually write out a function for CADE. And I think a reason behind that is because how you want to build an algorithm to determine what's an outlier, what's not, what's real data, what's fake data, is completely up to you. So I've written a very basic way of doing things here. All I've done here is take, again, my income and my coverage to income ratio variable. I've put a uniform distribution using the random.uniform function from NumPy, and essentially built a uniform distribution around those variables. Great. Now I have essentially fake data. I have real data. I can combine them together. And then essentially, I'm just going to use a random forest classifier here to just try and predict that target, where the target is real versus fake. And all I'm looking at is the predicted probabilities outside of that target. That's what I use to be able to build this plot here. The ones with the higher predicted probabilities are the bigger circles, the lower predicted probabilities, the lower circles. So I know we're running a little short on time, but thank you all very, very much for coming out. Maybe we can do this in person next time. I know Murat said that we do this online, which is great, but I hope to meet you guys in person one day as well. So like I said, feel free to connect with me. Feel free to email me if you have any questions. More than happy to talk with any of you guys. In fact, again, thank you very much, Murat. I didn't know if you wanted me to continue answering questions or what you wanted the next steps to be.
Please, just if you feel like you have time to do that, you can ask us questions. We have Q&A 11.
Sure. Yeah, no problem at all.
Yeah.
So let's see here. In what situations would you recommend one of the three methods you discussed over the other two? Oh, man. That's a hard one because the problem ahead of time is we don't know what one would discover as compared to another. So what I would actually recommend, if you have time, is actually to run all three. The best part is they may each find different things. Now, there are some observations that we saw in the three different plots that they all agreed upon. These were all outliers. Okay, good. Well, that's a good thing for you. You go, okay, I have a lot of confidence that this is an anomaly. But one of the techniques may be able to find something that another would not. And so that's where the value comes in of trying to run all of them. I think the benefit of something like CADE really is the notion that you can use any variables you'd like. So in isolation forests, as well as with local outlier factor, they work well in a multidimensional space that doesn't have categorical variables. It's really more of a multidimensional space that has continuous data and has clouds of continuous data. CADE is not restricted by that. All we're doing with CADE is we're just randomly creating new data. We can randomly create a uniform distribution on a categorical variable. We can put that categorical variable into a random forest classifier, for example, and use that actually in our prediction for what's real and what's fake. And so that's why I find the value in CADE is it's not limited just to continuous variables, but I find that all of them still have some value in them. Let's see here. How do you take advantage of known cases, normal or anomaly, like sort of an enforcement operation? Well, the advantage you're taking here of these known cases is sort of, that idea of normal is that notion of, all right, once you define what normal is, you're sort of trying to train these algorithms into finding things that aren't that. And so when you're looking at things that aren't normal, that's where you're trying to be able to identify something that doesn't follow the normal pattern of what we're looking at. Are the three methods you discussed better than neural networks for anomaly detection? This is the best part. It depends on the data set. I think these are a little bit more interpretable potentially than a neural network. I think neural networks have value, but sometimes neural networks can take a long time to train. These aren't necessarily very time intensive. And so you might be able to still find those big anomalies without having to go through all the intense training of a neural network. Not saying that neural networks are bad. They're still good too. There's just a variety of different ways of being able to solve the problem. And so how do these methods perform for anomalies in streaming data? Are there better methods you would recommend for streaming use cases? So in a streaming data world, that becomes a little bit more difficult. And so, for example, in trying to build these things in a data cloud in a streaming sense, it really is now trying to be able to figure out what is abnormal compared to what I've seen potentially just recently, not even across all of time, just potentially recently. So in a streaming sense, a lot of times it would be more along the lines of being able to try and find a pattern over time. And so being able to see if something has gone out of pattern over time as compared to just sort of out of pattern overall. I mean, you might be able to do something like a CADE, where again, each new observation that comes in, you can just score it. You can get a predicted probability. This observation doesn't look like any of the rest. But really what you're doing in that streaming scenario, though, is you're scoring as you're going more than you are truly updating the model as you go. So hopefully, Avi, that helps answer that question. So I would be interested to know in multidimensional data which variable actually caused the outlier. Ah, that's a wonderful, wonderful comment. And that's actually one of the values of CADE. So the nice part, Surinder, of using something like CADE, if you think about it, let me go back even to here. I built it off of a random forest. Well, wait a minute. Random forests have variable importance. I can look and see what variables drove the detection of the anomalies. In fact, I can even go down to individualized predictions and see which variables drove that prediction on why that point was specifically an anomaly. Again, one of the values of CADE, being able to actually break down what variables are driving something to be an anomaly as compared to something else. Perfect. Well, I think that answers all the questions that were on there. Again, thank you all so much. It's been an absolute pleasure being able to be here. Thank you all for the invitation. You know, I'd love to do one of these again if you guys are interested. That is no problem at all. Again, feel free to connect with me anywhere you'd like.
Great, Aric. That was lovely and fantastic presentation. I appreciate on behalf of everyone. So we love to host you again. I mean, people enjoy and they have great feedback. So
awesome.
we love to see you again.
Sounds
so I'd
good,
like to connect you on site. I have some ideas to work with. Maybe we can discuss that later. I will send you the email.
Perfect. Sounds wonderful.
Thank you. Have a good day, everyone. Thank you for participating.
Thank you. Take care.
Bye.